Chapter 35, Diffraction. Units of Chapter 35 include diffraction by a single slit or disk, intensity in single slit diffraction pattern, diffraction in the double slit experiment, limits of resolution, circular aperture, resolution of telescope and microscopes, the lambda limit, resolution of the human eye and useful magnification, diffraction grading, the spectrometer and spectroscopy, peak width and resolving power for diffraction grading, X-rays and X-ray diffraction. Section 1. Diffraction by a single slit or disk. If light is a wave, it will diffract around a single slit or obstacle. Light, which here we can consider as waves, and it's being blocked by a solid disk. As we expect, we will have shadow formed on the screen, but at the center we can have a bright spot due to the wave nature of light. This is called diffraction. The resulting pattern of light and dark stripes is called the diffraction pattern. This is the shadow of the disk I mentioned, which forms a black area of darkness. But near the edges of the shadow, we will see stripes. At the center, we'll see a bright spot. As we go into the light area, we will see lines of diffraction pattern. Also, if the light is being blocked with a razor blade, at the middle point, we will have diffraction patterns in different angles, and bright and dark spots of diffraction pattern will be formed. Also, if the light is passing through a single slit, we will have bright and dark stripes of diffraction pattern. This pattern arises because different points along a slit create wavelets that interfere with each other, just as a double slit would. So if you have a single slit, some angle, different portion of the light will have different optical path lengths related to the angle of incidence of sine theta. For the dark spot, we have sine theta is equal to lambda over d, and for brighter spot we have, for example, 3/2 lambda over d. D is the size of the slit, lambda is the wavelength. So this is one integer, lambda over d. This is 2 multiplied by lambda over d. The minima of the single slit diffraction pattern occur when d times sine theta, d is the size of the slit, times sine theta is equal to integer m multiplied by lambda. The minima happen at the integer multiplication of lambda over d ratio. As an example, let's go through problem number 8 in the book. For a given wavelength lambda, what is the minimum slit width for which there will be no diffraction minimum? What is the minimum slit width so that no visible light exhibits a diffraction minimum? For section A, there will be no diffraction minima. So let's write down no diffraction minima if the angle of the first minimum is greater than 90 degrees. So we set the angle in equation 35. Equation 35-1 equal to 90 degrees, and solve for the slit widths. So we have sine theta is equal to lambda over d. Solve it for size d, lambda over sine theta, and we said for theta equal 90 degree, sine theta equals 1. So we have d equal lambda. For part B, if we want no visible light to exhibit a diffraction minimum, the slit widths must be equal to the shortest visible wavelengths. And the shortest visible wavelengths is 400 nanometer. So we say D is equal to lambda minimum, and that is equal to 400 nanometer. Section 2. Intensity in single slit diffraction pattern. Light passing through a single slit can be divided into a series of narrower strips. Each contributes the same amplitude to the total intensity on the screen, but the phases differ due to the differing path lengths. So delta beta, the difference in the path lengths, is equal to 2 pi over lambda times delta lambda times sine theta. So if light is coming through such a single slit structure at an angle theta, this is the delta y, and we have different optical path lengths of delta y times sine theta between different components of the light. And the largest optical path length is equal to d times sine theta. Phasor diagrams give us the intensity as a function of angle. So here, if we have n strips, for the case when we're looking at the center, there's no angle. All the vector components of the phasors for n strips will be lined up, and they will add in superposition of all the vectors. They add up and multiply by n times delta E naught. For the case when we are looking at a point between the center and the first minimum, we're introducing a delta beta phase difference between the phasors. Introduce some optical path difference between the entering point and on the point on the screen. For the case of a first minimum, all the phasors or the wavelets, they have a beta equals 2 pi or 360 degrees, and E theta, or the intensity at that point, is equal to 0, and that forms the first minimum. For the case of near secondary maximum, beta is different than 2 pi, and we still have some intensity at the point near the secondary maximum. So we successively add components of these wavelets, and for the case of first minimum, they overlap and they reach to the first one, so it will form a minimum or dark spot. But for a near secondary maximum, it forms a non-zero point. The intensity is lower, and it's a vector sum of all the components of the wavelets or the strips. Taking the limit as the width becomes infinitesimally small gives the field as a function of angle. So if those wavelets or strips are infinitesimally small, you'll have a curve, and E theta, the intensity at point and angle theta, is equal to E naught multiplied by sine of quantity beta half divided by the quantity beta half, and beta is the angle of diffraction. Finally, we have the phase difference and the intensity as a function of angle. So the phase difference beta is equal to 2 pi divided by lambda multiplied by d times sine theta, and I theta is equal to I naught multiplied by the quantity sine beta over 2 divided by beta over 2 squared. Section 3. Diffraction in the double slit experiment. The double slit experiment also exhibits diffraction effects as the slits have finite widths. This means the amplitude at an angle theta will be modified by the same factor as in the single slit experiment. So E theta naught is equal to 2E naught multiplied by sine of beta half divided by beta half times cosine of delta half, where delta is 2 pi times d times sine theta over lambda. The intensity is actually proportional to the square of the field, and it's equal to I naught multiplied by the quantity of sine beta half divided by beta over 2 squared multiplied by cosine squared of delta half. The diffraction factor, which depends on beta, appears as an envelope modifying the more rapidly varying interference factor, which depends on little delta. So the first plot is the diffraction factor versus angle theta, and there's a relation of sine squared beta half divided by beta half squared. And then for part B, we see the interference factor of cos squared delta half versus angle theta. And the third one is a convolution between these two, diffraction and interference pattern. And you will have interference, which is convoluted with an envelope, which is showing as a diffraction. Section 4. Limits of resolution, circular apertures. Resolution is the distance at which a lens can barely distinguish two separate objects. Resolution is limited by aberrations and by diffraction. Aberrations can be minimized, but diffraction is avoidable, and it is due to the size of the lens compared to the wavelength of the light. For a circular aperture of diameter d, the central maximum has an angular width of theta equals 1.22 times lambda divided by d, where theta is in radians. The Rayleigh criterion states that two images are just resolvable when the center of one peak is over the first minimum of the other one. So if you have two objects separated by distance s, and they're placed at locations O and O prime, the rays of light coming from these 2 points forming angle theta, and they reach to the screen and they form two diffraction patterns. And we can resolve these two centers when the peak of one of them is happening at the minimum of the image of the other source. That's the distance which defines the Rayleigh criterion for resolving two objects, or defines the resolution of this optical system. For telescopes, the resolution limit is as we have defined it. Theta is equal to 1.22 times lambda over d, and theta is in radians. For microscopes, assuming the object is at the focal point, the resolving power is given by RP, resolving power, is equal to S, is equal to F, the focal point, multiplied by theta, and theta is obtained from here, so we have 1.22 times lambda times F divided by D. Typically, the focal length of a microscope lens is half its diameter, which shows that it is not possible to resolve details smaller than the wavelengths being used. So for such a scenario where the focal length is half of the diameter, so focal lengths cancel out, and resolution power is half of the wavelengths of the light probing the sample. Section 6. Resolution of the human eye and useful magnification. The human eye can resolve objects that are about 1 centimeter apart at a distance of 20 meters, or 0.1 millimeter apart at the near point. This limits the useful magnification of a light microscope to about 500x to 1000x. Section 7. Diffraction grating. A diffraction grating consists of a large number of equally spaced narrow slits or lines. A transmission grating has slits, while a reflection grating has lines that reflect light. The more lines or slits there are, the narrower the peaks. So we have broader and wider peaks for the case when we have less number of lines or slits. And when we have more lines or slits, we have narrower peaks for diffraction from the diffraction grating. For a diffraction grating, the maxima of the diffraction pattern are defined by sine theta equals m lambda over d, where m is an integer starting from 0, and this is for the diffraction grating for principal maxima. So no matter what wavelength is, for m equals 0, at the center we have a bright spot, but for blue spot we have 400 nanometer, another one at another 400 nanometer, for the red every 700 nanometer separation. We can have a rainbow structure. For the case of a white light, we have all the wavelengths included. So we have a spectrum from blue to red for the first diffraction order. For the second diffraction order, we have a fainter rainbow, which is spread more. And these diffraction orders are symmetrically distributed around the center. Alright, let's look at a couple of examples and problems from the book. First, I'll look at problem number 24 in the book, which asks, what is the resolving power of a microscope at the wavelengths lambda equal 500 nanometer with a 5 millimeter diameter objective, which has objective with focal lengths of 8 millimeter. The resolving power of microscope is given by equation 3511, 1.22 multiplied by lambda times f divided by d. Let's plug in the values. So resolving power is equal to 1.22 550 nanometer. The focal length is 8 millimeter, and the diameter is 5 millimeter, and that gives us 1074 nanometer, which is almost equal to 1 micrometer. Another example, problem number 28 from the book. Suppose that you wish to construct a telescope that can resolve features 6.5 kilometers across on the moon, 384,000 kilometers away. You have a 2 meter focal length objective lens whose diameter is 11 centimeter. What focal length eyepiece is needed if your eye can resolve objects 0.1 millimeter apart at a distance of 25 centimeter? And what is the resolution limit set by the size of the objective lens, that is the diffraction, and you have to use lambda equals 560 nanometer. To find the focal length of the eyepiece, we use equation 33-7, which says the ratio of focal lengths, the objective, the focal length of the eyepiece is equal to theta prime over theta, where theta prime is the ratio of the minimum resolved distance and 25 centimeter. Let's write it down. Minimum resolved distance at 25 centimeter. And theta is the ratio of the object on the moon and the distance to the moon. So for theta, we have ratio of the object on the moon and the distance on the moon. So we can write this one as d over n. The other one we have dO over L. So let's plug in the values. We can also ignore the fact that the image is inverted, so we can solve it for the focal length of the eyepiece is equal to the focal length of the objective multiplied by theta divided by theta prime. That is equal to f objective times d objective over L D over N. If you plug in the values, 2 meter times 6.5 kilometer over 384,000 kilometer divided by 0.1 millimeter divided by 250 millimeter. That simplifies to 0.0846 meter, which is almost 8.5 centimeter. So that's the focal length of the eyepiece. To find the resolution limit, let's use equation 35-10. Theta is equal to 1.22 lambda over d is equal to 1.22. Wavelength is 560 times 10 to the power minus 9 meter divided by 0.11 meter, and that gives us 6.2 times 10 to the power minus 6 radian. This corresponds to a minimum resolution distance R. Write down minimum resolution distance R is equal to 384,000 kilometers multiplied by 6.2 times 10 to the power minus 6 radian, which results to 0.4 kilometers, which is smaller than the 6.5 kilometer object that we want to observe. Therefore, this telescope can resolve such an object. Okay, now let's look at problem number 32 in the book as another example. When driving at night, your eye's pupils have dilated to a 7.5 millimeter diameter. If your vision is diffraction limited, what would be the greatest distance at which you could resolve the two headlights of an oncoming car, which are spaced 1.5 meters apart? Assume a wavelength of 550 nanometer for the light. If we assume that our eyes are diffraction limited, we can use the Rayleigh criteria and equation 35-10. Assuming our vision is diffraction limited, so for diffraction limited vision, we use Rayleigh criterion and equation 35-10, which says theta is equal to 1.22 lambda divided by d. Also, this angle is given by the separation of the headlights divided by distance of the headlights. So, separation of the headlights divided by the distance to the headlights. We should call it S over L. Now we can solve it for L is equal to d times S divided by 1.22 times lambda. And if you plug in the values, you have 7.5 times 10 to the power minus 3 meter multiplied by 1.5 meter separation between the headlights divided by 1.22 times 550 times 10 to the power minus 9 meter, the wavelengths. That simplifies to 16,770 meter, which is almost 17 kilometers. That's the farthest distance we can resolve the two headlights. Section 8. The spectrometer and spectroscopy. Spectrometer makes accurate measurements of wavelengths using a diffraction grating or prism. So this is the cartoon of a spectrometer. We have a source of light that we want to measure and determine the wavelengths of the source light. The light passes through a collimator and shines on a grating. The grating pattern will diffract the light, and by rotating the telescope we can scan through different angles and see the intensity of the light being diffracted at different angles. And by doing the calculations for different diffraction orders, we can calculate the wavelengths of the input light. The wavelengths can be determined to high accuracy by measuring the angle at which the light is diffracted. So sine theta is equal to integer m times wavelengths lambda divided by d. This is for diffraction grating, for principal maxima, for different orders of integer m's starting from 0. Atoms and molecules can be identified when they are in a thin gas through their characteristic emission lines. Here, for example, we have atomic hydrogen, which consists of blue lines, some traces from the red line. Mercury is composed of blue, some green, 2 lines of yellow, 3 lines of red. For sodium, we only have yellow lines. For solar absorption spectrum, we have all the white light, but some lines are missing, representing absorption of those wavelengths. Section 9. Peak widths and resolving power of a diffraction grating. These two sets of diagrams show the phasor relationships at the central maximum and at the first minimum for gratings of 2 and 6 slits. So when we have 2 slits, we have 2 phasors. For the central maximum, theta is 0, so they are vectorially added to the maximum intensity. For the minimum, the angle between these two phasors is 180 degrees, so the final intensity is 0. For the case of 6 slits, we have 6 phasors. At central maximum, when theta is 0, there's no phase difference between these slits or these phasors. They all add up and have maximum intensity E0. But for the minimum, these 6 slits, they have to vectorially add to total intensity of 0. Therefore, we will have a phase difference of 60 degrees between the light fields from each slit. As the number of slits becomes large, the width of the central maximum becomes very narrow. So delta theta naught is the width of the central maximum, is equal to lambda divided by n times d. Therefore, for larger n, we have narrower delta theta. The resolving power of a diffraction grating is the minimum difference between wavelengths that can be distinguished. So R, the resolving power for a diffraction grating, is equal to the ratio between lambda over delta lambda, that is equal to n times m. Okay, let's take a look at problem number 38 in the book as an example. White light containing wavelengths from 410 nanometer to 750 nanometer falls on a grating with 7,800 slits per centimeter. How wide is the first order spectrum on a screen 2.5 meters away? So, to solve this problem, we use equation 3513 to find the first order angles for the maximum and the minimum wavelengths, which says d sine theta is equal to m times lambda, where the slit separation distance is the inverse of the number of lines per centimeter. So let's write it down. D slit separation distance is equal to 1 over number of lines per centimeter. Number of lines per centimeter. So let's use these two equations and solve it for angle theta, which which is inverse sine m lambda over d, and d is equal to 1 over n. So we have sine inverse m lambda n. Okay, so we solve it for theta 1. We have inverse sine of 410 times 10 to the power minus 7 centimeter multiplied by 7,800 lines per centimeter, and that gives us 18.65 degrees. For theta 2, we have inverse sine 750 times 10 to the power minus 7 centimeter times 7,800 lines per centimeter is equal to 35.8 degrees. So these are the angles at which we have the central maximum of minimum and maximum wavelengths. Okay, so we should set the distance between these two central maxima to the distance to the screen multiplied by the tangent of the first order angle. So we have delta y is equal to y2 minus y1 L times tan of the quantity theta 2 minus tan of quantity theta 1. Let's plug in the values. So we have 2.5 meter multiplied by tan 35.8 degrees minus tan of 18.65 degrees, and that results in 0.96 meter. Another example, I look at problem number 44 in the book. The first order line of 589 nanometer light falling on a diffraction grating is observed at 15.5 degrees angle. How far apart are the slits? At what angle will the third order be observed? So for the slit separation width D, we solve equation 35-13. So we have d times sine theta is equal to m lambda. Solve it for separation of the slits d. M lambda divided by sine theta. Let's plug in the values. We have the first order 1 for m. The wavelength is 589 nanometer, and we have sine of 15.5 degrees. That results in 22.4 nanometer, which is almost 2.2 micrometer. For the angle for the third order, we know m is equal to 3, and we should solve the same equation for theta is equal to sine inverse m lambda divided by d. So from the previous part, we know d. So plug in the values. Sine inverse m is 3, lambda is 589 nanometer, and from previous section 2204 nanometer, and that results in 53.3 degrees. Section 10, X-rays and X-ray diffraction. The wavelengths of X-rays are very short. Diffraction experiments are impossible to do with conventional diffraction gratings. Crystals have spacing between their layers that is ideal for diffracting X-rays. So here we have a cartoon, gray spots showing atomic or molecular crystalline structure of a material where it can diffract X-rays, and we can have diffraction pattern, and from those diffraction we can identify and measure the size and the crystal structure. Therefore, X-ray diffraction is now used to study the internal structure of crystals. This is how the helical structure of DNA was determined. Okay, as an example, let's go through problem number 50 in the book. A 6500 slit per centimeter diffraction grating is 3.26 centimeter wide. If light with wavelengths near 624 nanometer falls on the grating, how close can two wavelengths be if they are to be resolved in any order? What order gives the best resolution? So we start with equation 35-13 again. D sine theta is equal to m lambda, and we use this equation to solve for m d sine theta over lambda, and that gives the maximum order possible for this diffraction grating by setting the angle of theta equals 90 degrees. So theta equals 90 degrees. That's a maximum diffraction order. So m is equal to d divided by lambda, and if we plug in the values, m is equal to 0.01 meter divided by 6500 lines divided by 624 times 10 to the power minus 9 meter as the wavelengths. That simplifies to 2.47, but we want to see the maximum diffraction order. We round it down to order number 2 is the maximum diffraction order. For the order at which we will have the best resolution, we have to use the equation for the resolving power, and we put the resolving power equal to the product of the number of grating lines and the order, where the resolving power is the wavelengths divided by the minimum separation in wavelengths, and solve for the separation. So we have lambda over delta lambda is equal to n times m. Solve it for delta lambda is equal to lambda divided by n times m. Lambda is 624 nanometer, n is 6500 lines per centimeter, and we have 3.26 centimeter, and we have the second order, and that gives us delta lambda is equal to 0.015 nanometer. So since the second order is more spread out than the first order, the resolution is the best for the second order. Also, the value of delta lambda is smaller for m equal 2 than m equal 1. Therefore, the resolution is the best for m equals 2 as a second order. Another example, problem number 54 in the book. First order Bragg diffraction is observed at 23.6 degrees relative to the crystal surface, with spacing between atoms of 0.24 nanometer. A asks at what angle will second order be observed, and B asks what is the wavelengths of the X-ray. So we use equation 35-20 for the X-ray for both orders of diffraction. So we say m times lambda is equal to 2d sine phi. So if we use the same equation for two orders of magnitude and take the ratio, we have m1 divided by m2 is equal to sine of angle phi 1 divided by sine of angle phi 2. Solve it for angle phi 2 is equal to sine inverse of m2 divided by m1 times sine phi 1. Let's plug in the values. Phi is equal to sine inverse of the second order divided by 1. The first order, m equal multiplied by sine of 23.6 degrees. That simplifies to 53.2 degrees. For the wavelengths of the, so that was part A. For part B, as the wavelengths of the X-ray, we use the first order data and we say m times lambda is equal to 2d sine phi, and solve it for lambda is equal to 2d sine 5 divided by m, and if you plug in the values, we have 2 times 0.24 nanometer times sine of 23.6 degrees divided by the first order m equals 1. Therefore, lambda is equal to 0.19 nanometer. Summary of Chapter 35. Light bends around obstacles and openings in its path, yielding diffraction patterns. Light passing through a narrow slit will produce a central bright maximum of widths sine theta equals lambda over d for the first minimum, and minima occur at d times sine theta is equal to m times lambda for integer m starting from plus minus 1. Diffraction limits the resolution of images. Diffraction grating has many parallel slits or lines. Peaks of constructive interference are given by sine theta equals m times lambda divided by d for diffraction grating, and principal maxima and integer m starts at 0.